Today we're going to talk about a powerful, pretty much invisible force that is literally shaping the world around us. And I mean everything, from the tallest skyscrapers to that stubborn jar of pickles in your kitchen. So let's get right into it. Okay, so picture this. You're driving over a big bridge, and you hear that rhythmic thump-thump, thump-thump sound from your tires. You ever wonder what that is? If you look, you'll see these weird, almost teeth-like gaps in the road. And no, it's not a mistake. It's actually a stroke of genius. These things are called expansion joints. And what they do is give these massive structures the space they need to, well, breathe. Without them, on a really hot summer day, all that metal and concrete would expand and could literally tear the bridge apart under its own force. And believe it or not, it's the exact same science that solves that classic kitchen nightmare. You know the one? You've got a jar lid that is just completely stuck. So what do? You run that metal lid under some hot water for a second and pop, it twists off like it was nothing. So what is the connection between a giant bridge and a tiny pickle jar? Well, we're looking at an everyday puzzle that has a really, really cool scientific explanation. The answer, my friends, is thermal expansion. It's this fundamental tendency for things to get bigger when they heat up and smaller when they cool down. It happens all around us in solids, liquids, and gases. And once you know what you're looking for, you start seeing it absolutely everywhere. But how does this actually work? I mean, why does heat change the size of things? Let's dig into the science here. So, the official definition is that thermal expansion is the tendency of matter to change its shape, area, and volume when the temperature changes. But let's be real, what that really means is heat makes stuff bigger, cold makes stuff smaller. But the big question is, why? It all happens at the atomic level. See, everything is made of atoms and molecules that are just constantly vibrating, constantly moving. When something's cool, its particles are kind of huddled together, vibrating pretty gently. But when you add heat, you're just adding energy. And those particles start vibrating like crazy, pushing each other away and taking up way more space. Let's zoom in even closer on this little microscopic dance, because there's one more detail here that is just absolutely crucial to the whole story. I just love this analogy. Think of all the atoms in a solid object, like people packed into a quiet room. Now, turn on the music, add some heat, and everybody starts to dance. They need more elbow room, right? And as they spread out, the whole room, the whole object gets bigger. But here's the real kicker. You'd think that as the atoms vibrate, they'd move in and out an equal amount, kind of keeping their average position the same. But they don't. The forces between them are asymmetric. It's a bit like a one-way street. It's way harder to shove them closer together than it is for them to drift farther apart. So as they get more energy and vibrate more, their average distance actually increases. And that's what makes the material expand. Okay, so now that we get the why at the atomic level, we can zoom back out and really appreciate the what and where in the world all around us. You'll see this principle is just everywhere. Seriously, once you see it, you can't unsee it. Those power lines hanging between poles, they're intentionally left a little slack because they shrink in the cold winter and could snap. On a hot day, they expand and sag down. Railroad tracks can expand so much they can actually buckle into this dangerous shape called a sun kink. And get this, the Eiffel Tower is about 15 centimeters, that's like 6 inches, taller in the summer than it is in the dead of winter. Now, don't let the formula on the screen scare you. You don't need to be a physicist here. It's actually really simple. How much something grows, that's the delta L, depends on just 3 things. First, what's it made of? That's the little alpha symbol. Second, how big was it to begin with? That's L0. And third, how much did the temperature change? That's delta T. Simple as that. And that first thing we mentioned, what the material is so incredibly important. Just look at this chart. You've got Pyrex glass, which barely expands at all. That's why you can pull a hot dish out of the oven and it doesn't shatter. But then look at aluminum. It expands about twice as much as steel does for the same change in temperature. You can see why engineers have to be so careful about the materials they choose for a job. And of course, it isn't just solids. That old-school thermometer, it works because the liquid mercury inside expands when it gets warmer, which forces it up that tiny glass tube. And a hot air balloon is the perfect example for gases. You heat the air inside, it expands, it becomes less dense than the cooler air outside, and that difference creates the lift that sends the whole thing soaring. So the rule seems simple, universal, right? Heat expands, cold contracts. But, nature loves a good plot twist, and that brings us to water's really weird an incredibly important exception to the rule. So we've got it all figured out. Heating expands, cooling contracts. It's a law of physics. It applies to pretty much everything. Or does it? Well, here's where it gets weird. Water is a total rebel. With most liquids, as you cool them, they just get denser and denser and denser. But water does this bizarre thing. As it cools from 4 degrees Celsius down to freezing at 0 degrees, it actually starts to expand again. It gets less dense. The reason why is all down to these things called hydrogen bonds. As water molecules get really cold, these bonds lock them into place in a very specific, open crystal structure. And that rigid structure actually takes up more space than when the molecules are just jumbled up and flowing around as a liquid. It's the exact reason why ice cubes float in your drink instead of sinking to the bottom. Now, this isn't just a cool science fact. It is absolutely critical for life on Earth. Think about a lake in the winter. The water at the surface cools down, gets denser, and sinks until the whole lake is about 4 degrees Celsius. But then, as the surface water keeps getting colder, it becomes less dense, so it stays right there on top. It freezes at 0 degrees, and that layer of floating ice acts like a perfect blanket, insulating the liquid water underneath and letting fish and everything else survive the winter. If water didn't do this, lakes would freeze solid from the bottom up. So when you really think about it, that tiny, invisible dance of atoms has this huge, macroscopic consequences. We have to design our entire world around it, and nature itself has used it to protect life. And that leaves us with one final, pretty big thought. We've seen how much a solid tower or a gas can expand. Now, imagine that same principle applied to the absolutely immense volume of water in our oceans. What do you think the global impact is when all of that water warms up and expands, even by just a tiny, tiny fraction? Definitely something to think about. Thanks for joining me.